on to the next lecture. It's work of Paul Hecking from the University of Massachusetts at Amherst and Shan Qiu from the University of Texas at Austin. But it's Paul Hecking who's going to talk to us on mirror symmetry and cluster algebras.
I'm going to report on joint work with Sean Keel and also Mark Gross, Maxim Kontsevich, and Bernd Sievert. Let me give the goals of the talk. So the first goal, I'm going to explain what is a cluster variety. Secondly, talk about mirror symmetry for certain non-compact Calabi-Yau varieties following work of Denis Héroux. And thirdly, the construction of a canonical basis of the algebra of global functions on a cluster variety, the so-called cluster algebra, using mirror symmetry methods. So this gives a proof of conjectures of Fomin-Zelevinsky and Goncharov. So that's the plan. And just to give you some idea, unfortunately I won't be able to talk about this application in the talk, but just to give you some idea why they might be interested in this, a sort of sample application of the third item is the construction of canonical bases for irreducible representations of SLN, which have some enumerative information, Gromov-Witten invariants, encoded in them. And it seems very likely that these bases coincide with those constructed by Lustig and Kashiwara. Maybe the main evidence for that is the close connection of both with quantum groups. Okay, so let's begin with log Calabi-Yau varieties. So this is a version of a non-compact Calabi-Yau. So we have a smooth projective variety will always work over the complex numbers, let's say it's dimension n, and a normal crossing divisor on x, which is anti-canonical. So kx plus d is equal to 0. And we'll call the complement u a log Calabi-Yau variety. So this is the class of non-compact Calabi-Yaus where mirror symmetry seems to work the best. So another way to say this is that we have a nowhere zero holomorphic form on u, which has simple poles along the boundary divisor, the so-called holomorphic volume form, uniquely determined up to a scalar. So a good example is the algebraic torus, C star to the n. So that's a log Calabi-Yau variety with a holomorphic volume form, the standard toric form written there. And if I take any toric compactification, so just an equivariant compactification for the torus action, that's a log Calabi-Yau pair. It satisfies kx plus d equals 0. So this example will be very important for us in this talk. Another way to get a log Calabi-Yau variety, so starting with a log Calabi-Yau pair, I can do some blow-ups of subvarieties contained in the boundary to get other examples. So specifically, I take a codimension 2 subvariety contained in a unique component of the boundary divisor, meeting the remaining components transversely. I blow it up, I take the strict transform of the divisor, and that gives me a second log Calabi-Yau pair, and this is what we'll call a non-toric blow-up. And so, giving a definition, the toric model, a toric model for a log Calabi-Yau variety is just an expression of that log Calabi-Yau starting with a toric pair and performing a sequence of non-toric blow-ups to arrive at our varieties. That's what we'll call a toric model. So here's a quick example. This is a toric model for P2 with a line and a conic meeting transversely removed. So the first, going from left to right, the first two birational transformations, I'm just blowing up boundary strata. I'm not changing the interior U there by those transformations. But when I arrive at the third surface there, you can see there's an internal -1 curve. That's the strict transform of a tangent line to the conic. That can be blown down, and this map marked F in the diagram is then a toric model for this log Calabi-Yau. We're blowing down to the Herzebruch surface F2. Okay, so we can now make a definition, so-called maximal log Calabi-Yau variety. That's just a variety that when we compactify, the boundary has a zero-dimensional stratum, so a point cut out by n analytic branches of the divisor, n being the dimension. So that's obviously a necessary condition to have a toric model to be obtained as a blow-up of a toric variety. And in fact, in dimension 2, that's sufficient. That's a nice exercise in the birational geometry of surfaces. Although you probably won't be surprised to learn it's not true in higher dimensions. because, for instance, Fano varieties are typically irrational in higher dimensions. So, for instance, you can construct a counterexample that's birational to a cubic threefold. So now I can tell you what a cluster variety is. So it's a special type of log Calabi-Yau variety and has the following two properties. So first of all, in addition to the holomorphic volume form, we have a non-degenerate holomorphic two form. So a cluster variety, very roughly speaking, something like a log hyperkähler variety or log holomorphic symplectic variety. And this form should have, as usual, as before, controlled behavior at the boundaries, which have logarithmic poles along the boundary of any log Calabi-Yau compactification. And here, let me just remind you, when we talk about differentials with logarithmic poles, I just mean I allow terms of the form dz over z, where z is a defining equation of one of the boundary divisors. And the second condition is that we also have a toric model. So this is obtained as a blow-up of a toric variety in the way we previously discussed. Okay, and let me add this remark for anybody that's familiar with the theory of cluster algebras. It's usually the case that you allow the form to be degenerate. But from our point of view, the non-degenerate case is the essential one. The other cases can be deduced from it. And also mirror symmetry is somehow more natural in the case where you restrict to the non-degenerate case. So we'll do that in this talk. Okay, so let's talk a little bit about the toric model of a cluster variety. So let's use the notation above. Oops. So the presence of this log2 form constrains the possible centers that we can blow up along. In fact, the centers must just be given by the following equation. So it's the closure of a hypersurface defined by a level set of a character, sort of a closure of a hypertorus, if you like, in the interior of the toric variety, intersected with a boundary divisor. And so maybe I'll skip this remark for a second and just say one way to think about this is that if you've just got a single blow-up, it's just the same as the two-dimensional case where I'm blowing up a point in the boundary, but then product with a trivial factor of dimension n-2, the algebraic torus of dimension n-2. So that's sort of the picture for a single blow-up. But then, of course, I'm doing several different blow-ups to create my cluster variety, blowing up several different centers. So it doesn't globally decompose as a product, but somehow the picture for a single center is no harder than dimension 2. And so just to come back to this parenthetical remark, how do you see this fact? Roughly speaking, what you do is you first use the following criterion. You look at the induced holomorphic 2 form on X bar, the toric variety. Now the condition that lifts to a log 2 form above is that when you take the residue along the boundary divisor, that has to restrict to 0 on the center. That's just an easy sort of discrepancy type calculation. But if you know a little bit about toric varieties, a log form on a toric variety automatically has constant coefficients. Those are the global sections of the sheaf of holomorphic forms, log forms. And so then you can see rather quickly that z has to be given by a character, and the residue up to a scalar is just the corresponding logarithmic differential. Okay, so let me now connect that with the original description of a cluster variety due to Fomin, Zelevinsky, and Goncharov. So this was the following definition. The variety is a union of a collection of open sets, a countable collection. They're all copies of a fixed algebraic torus, C star to the n. And they're glued by some maps which were called mutations, given, at least in some choice of coordinates on the torus, by the following simple formula. Okay, so how does that connect with our picture in terms of toric models? So first of all, if I have a toric model, recall I'm blowing up centers in the boundary, so it's an isomorphism over the torus. So I certainly get an open embedding of the torus in my variety U just by the inverse of this map. And so that's the picture. Where does this atlas of tori come from? They all correspond to different toric models of my cluster variety. And secondly, the mutations, these should be very familiar to algebraic geometers. They just correspond to the birational transformations given by elementary transformations of P1 bundles. And again, this is a picture that I think every algebraic geometer is familiar with in dimension 2, elementary transformations of ruled surfaces. And here again, it's no harder. We've just got a sort of trivial n-2 dimensional direction, just the product with a trivial torus of dimension n-2 times the usual elementary transformation in dimension 2. So again, I've drawn a picture, but I'm sure everybody's familiar. Oops. Here's a elementary transformation of P1 bundles. That's what this mutation is doing. So you can imagine you have your cluster variety, has several different blowdowns to toric models, and they're connected by chains of these elementary transformations. Okay, so unfortunately, I'm going to have to use a certain amount of toric notation in the talk, so let's get it out of the way. So I've got an algebraic torus T. Associated to it, there are two lattices, N and M. So N is the lattice of co-characters, or equivalently, the first homology of the torus, and M is the lattice of characters, the dual lattice, or equivalently, the first co-homology. So in my setup for a cluster variety, remember I had a toric model, so I'm blowing up some centers on a toric, in the toric boundary of my toric variety x bar d bar, and that center was defined by the intersection with a boundary divisor f of a hypersurface defined by a character. So now in this notation, the boundary divisor corresponds to a primitive vector in the lattice of co-characters. That's the corresponding generator of the ray of the fan of the toric variety. And the character corresponds to an element of this lattice M. Again, it's primitive because this center is irreducible, and it pairs to 0 with the vector v. That's just the condition that the character is generically regular and non-zero along the boundary divisor. And so maybe I should just mention, let me see if I can do a pointer here. Where's that word? Yeah, so I'm using the multiplicative notation for characters here. So z to the m will denote the character corresponding to m when I want to emphasize the multiplicative structure. Okay, and so maybe this is the most important formula on the slide. So earlier I gave a description of the mutation, but here one can write it invariantly without choosing coordinates in the following way. So I'm just describing it in terms of the pullback of characters, and it's given by this simple formula. And I just want to point out that, the point is that this formula really only depends on m and v, and there's also this complex scalar c, which will not be so important to us. But somehow it's, the notation is associated to a character m and a co-character v. Okay, so let's go back to general log-Calabi-Yau varieties and talk about the so-called tropicalization, closely related to the so-called essential skeleton of the Berkovich space. So if I have a log-Calabi-Yau variety, let's pick a log-Calabi-Yau compactification such that the boundary is a simple normal crossing divisor. So by that I mean the components are smooth and every intersection is irreducible. Then the tropicalization of U is defined to be the cone over the dual complex of D. The dual complex of D being the simplicial complex with one vertex for each component of D and a simplex corresponding to each intersection of components of D. And we'll write this notation U trop Z. Sorry. Where did I go here? Here. Okay. We'll write this notation U trop Z for its integral points. I'll call that the tropical set. Okay, so here's a quick example. If I start with an algebraic torus, then it's easy to see this set is just the lattice of co-characters. Indeed, if I take any toric compactification, the cone over the dual complex of the boundary is just the fan of x in the vector space n tensor R. So that's sort of easy for the torus. However, I also want to give an intrinsic description of tropicalization. The way I described it earlier, it seems like it should depend on the compactification. In fact, it doesn't, and it can be characterized in this way. So a point in this tropical set, not 0, corresponds to a boundary divisor in some log-Calabi-Yau compactification together with a multiplicity. So that's going to be important for us later on. And here, of course, I identify two divisors in two compactifications if, under the corresponding birational map, one is mapped to the other. Okay, so it follows from this description that if I have any birational map between log-Calabi-Yau varieties that respects the holomorphic volume forms, then it gives an identification of the two tropical sets. So they just correspond by the intrinsic nature of the definition. And in fact, that's an integral piecewise linear identification. So that follows from factorization of birational maps. Okay, so let's give a quick example, the tropicalization of mutation. So let's just restrict to dimension 2, we won't lose anything. So the tropicalization in this case is the piecewise linear map given by these formulas. So it's the identity on the upper half plane, and it's a simple shear on the lower half plane. So here's a picture of the tropical mutation, and I've compactified to P1 cross P1 on the left, and if you remember, the mutation is given by an elementary transformation. So on the right, I've got F1, the Hertzsprung surface F1, and you can see that the tropicalization takes the fan of P1 cross P1 to the fan of F1. So that's sort of showing you how the boundary divisors relate in the two compactifications. Okay. Let's now state the main conjecture. So the first remark, which I'll come back to later, is that mirror symmetry for compact Calabi-Yaus does extend to the case of log-Calabi-Yau varieties, and I highly recommend the survey papers of Aru on this topic. So we have the following conjecture. So we take an affine maximal log-Calabi-Yau variety, and then our assertion is that the mirror is also of the same type, affine maximal log-Calabi-Yau, and we have a canonical basis of the coordinate ring of the mirror parameterized by the tropical set of the original variety. And this canonical basis is uniquely determined up to complex scalars, so independent complex scalars, one for each basis element. So a very good example of this conjecture is the case of the algebraic torus. So let's go back to that. If I have an algebraic torus, then the mirror is the dual algebraic torus. So I just dualize the first homology. So notice that means that the roles of the characters and the co-characters are interchanged when we pass from the torus to its dual. So then, and not surprisingly, the canonical basis of global functions on the algebraic torus is just given by the characters of the torus. And those, of course, can be characterized as the units of the ring, at least up to scalars. And this is the remark I just made. The characters of the dual torus, of course, are identified with the co-characters of the original torus, which, as we saw before, is just the tropical set. So this is a sort of simple case of the conjecture where it's really rather self-evident. Okay, but the main purpose of this talk is to explain a proof of the conjecture in the case of cluster varieties. And there, it's just that this special case of the conjecture is stated already in the works of Fomin Zelevinsky and Fock-Goncharov. In particular, Fock-Goncharov really introduced this tropical set into the picture. Okay. So let's, before we move on, let me briefly mention that there is a purely combinatorial construction of the mirror in the case of the cluster variety due to Fock-Goncharov. It's very simple, and I'd like to state it quickly. So if I have a cluster variety, let's just recall it's given as a union of copies of an algebraic torus. And these algebraic tori are glued by mutations which are associated to a choice of a character and a co-character of the torus. So here's a recipe for the mirror. We just take a copy of the dual torus, again indexed by the same set as the original U, and we reverse the roles of the character and the co-character. And there's also a sign that's introduced, keep doing that, sorry. There's also a sign that's introduced here that maybe I won't explain in full, but it's related to the choice of the two form. And just this remark at the bottom, you might be worried that the way I've defined it, it looks like this is not an involution. But in fact it is. If you take the double mirror, you get back to the original variety. It's just you have to compose with this isomorphism from the torus to itself given by the inverse map. Okay, so now let's review the Strominger-Yau-Zaslow formulation of mirror symmetry. So that conjecture asserts that mirror Calabi-Yaus, or log Calabi-Yaus in our case, admit dual Lagrangian torus fibrations. And so to a first approximation, what you can think of is that the mirror is a moduli space of pairs, L and nabla, where L is a real n-torus, a smooth fiber of F, and nabla is a rank 1 unitary local system on L, so corresponding to, sort of classified by its holonomy, which is an element of the dual real torus. So this point of view is partly inspired by the homological mirror symmetry conjecture. So with that in mind, we can define a naive complex structure on the mirror as follows. So if I take a smooth fiber of the original SYZ fibration on U, and I pick a cycle, gamma, a one cycle on that fiber, then for a nearby fiber, I can transport gamma to the nearby fiber, sweeping out a cylinder, and then define a local complex coordinate on the mirror in the following way. So this coordinate evaluated at the point corresponding to L with connection nabla is given by this formula. So it depends on the symplectic area of the cylinder and the holonomy of the local system around the boundary of this cylinder. And here omega, of course, is the Kähler form on our log Kähler BL. So taking a basis of the homology of the fiber over the base point and a small ball in the base, we get an open embedding of, actually this is a little typo, did it again. This is a little typo here, this should be G, these are coordinates on the mirror. We get an embedding, so these give local coordinates on the mirror. Okay, so here's a picture of the previous discussion. This is how the local coordinates on the mirror are defined. Okay, but that's not the correct complex structure, unfortunately. So somehow the problem is that there aren't enough functions, holomorphic functions, defined in a neighborhood of a singular fiber. The fact that you have monodromy means that the functions we just defined are not well defined in a neighborhood of a singular fiber. Okay, and so the solution to this, which goes back to the paper of Strominger, Yau, Zaslow, is that one needs to consider holomorphic disks in our variety U, which end on fibers of the SYZ fibration. And these give a correction to the complex structure. Those disks lie over codimension 1 walls in the base of the fibration, and so we have some gluing corrections as we cross one of these codimension 1 walls in the base. That's the picture we're going to pursue. So here's a picture of a SYZ fiber bounding a holomorphic disk in U, and the image in the base, I've tried to draw it here, is an amoeba-like object. Okay, so the basic fact about where does this canonical basis come from is that for the corrected complex structure, we expect global holomorphic functions on the mirror defined in the following way. So remember, if I have a point of the tropical set, it corresponds to a boundary divisor together with a multiplicity. And so I can make the following definition. I take a smooth fiber of my SYZ fibration F, and I consider holomorphic disks ending on that fiber, such that the holomorphic disk meets my given boundary divisor F in a single point with multiplicity K. It's otherwise disjoint from the boundary, and we also insist it passes through a mark point on the fiber. That's just to guarantee expected dimension 1. And now we make this definition here of a sum. So this is going to be a sum over such disks. And again, the terms in the sum, if we work in those local coordinates we discussed earlier, this will just be a constant, complex constant times the monomial we described earlier. So this is some power series in the local coordinates we had before. So I'm not claiming I know how to prove this converges or anything. This is just a heuristic discussion at this point. So here's a picture of a disk contributing to this global holomorphic function. Okay, so now what I want to do is describe a Roux example which sort of shows what the basic structure of this in the simplest case. So let's look at a toric pair given by just the plane with the coordinate axes and do a non-toric blow-up, just blow up a point on one of the coordinate axes. So we still have a residual S1 action on the blow-up. So let's choose a S1 invariant Kähler form on the blow-up, and let's let mu be the moment map. Then I can define a map from x to R2 given by the absolute value of the first coordinate squared and this moment map. And that defines a Lagrangian torus vibration on this log Calabi-Yau. And it has a unique singular fiber, a pinched torus, and the singular point of the singular fiber is just the S1 fixed point in the interior of U, in U. Okay, so in this picture we have a wall in the base defined by the absolute value of the first coordinate equal to 1. Each fiber over this wall bounds a holomorphic disk in U, which is contained in either the exceptional divisor or the strict transform of the line Z1 equals 1. So here's the picture. So we have these two red curves, the exceptional divisor and the strict transform of the line, are S1 invariant, so they map to a line in the base, this wall, and for any fiber over that wall, there's a disk which is a portion of one of those two curves which ends on that fiber. So that's a wall in the base associated to disks ending on fibers of the SYZ fibration. Okay, but let's continue. So actually choosing the Kähler form appropriately, so to be compactly supported in the neighborhood of the exceptional divisor, the change from the pullback, we can assume that the fibers are product tori away from the image of the exceptional divisor. So let's let L be such a fiber, and we're going to consider the disks ending on that fiber contributing to these theta functions that we defined, the theta function for the divisor D1. So on one side of the wall, there's just exactly one such disk given by this simple formula. But on the other side, in addition to that disk, there's another, which is the strict transform of a disk through the point we blow up. And it's given by this formula, which is easy to derive just using the Blaschke factors on the unit disk. So here's the picture of the extra disk. On the other side of the wall, we have this new disk that looks like this, and again, it will map to some sort of amoeba-like object in the base, which contributes to our theta function, evaluated at that point L with a connection nabla. And so now you can see this picture that we were discussing, that somehow if we were to just define these theta functions in the naive complex structure, they'd actually be discontinuous as you cross this wall. But the correction we add along this wall is exactly what's needed to make these functions actually continuous across the wall and in fact holomorphic. So this is the picture, I guess, originating with Gromov of a holomorphic disk bubbling off a holomorphic disk as we cross a wall. So the limit of this green disk in the picture as we approach the wall will be the standard disk we discussed earlier, together with this disk attached to the wall, the disk over the wall. Okay, so that's the sort of simplest example to motivate this heuristic construction of the theta functions. Okay, so now I want to switch gears and actually do this in algebraic geometry. So let's talk about the scattering diagram. So again, I'll have the usual notation for my cluster variety, a toric model, the torus, and so on. And let me remind you, the inclusion of the torus in U identifies the two tropical sets. So that's a piecewise linear identification. So I can identify my tropical set of U with the vector space associated to the code characters, n tensor R. So what we're going to do is define a so-called scattering diagram, D, in this vector space, which is associated to the cluster variety together with this choice of toric model. And the heuristic is that this is the tropicalization, so some kind of limit, of the collection of codimension walls in the base of the SYZ fibration we just discussed, corresponding to fibers bounding holomorphic disks in our cluster variety. And there'll be functions that are attached to those walls, which are essentially generating functions encoding counts of those disks. And so what are we going to do with this scattering diagram? Well, we'll use it to build the mirror cluster variety, just following the heuristic we just described. So there'll be these corrections as we cross the wall to the naive complex structure, and we'll also follow this computation of these global functions, theta q, but there'll be sort of a tropical version of this construction of counting these holomorphic disks to produce global functions on the mirror. Okay, so I need to make some definitions. What is a wall in the scattering diagram? So first of all, convergence is a delicate issue, as usual, especially in symplectic geometry. So we introduce formal parameters to control convergence, one for each center of the toric model. So we'll work over a base ring A, which is the polynomial ring in these variables, and in fact we'll have to complete at the maximal ideal. So what's a wall? Well, it's just the rational cone, a codimension 1 in our ambient vector space, together with an attached function, which will be a power series in a character for the dual torus, so corresponding to a point V in N, and that vector must lie in the span of the wall. And this function will be congruent to 1 modulo our maximal ideal. So this will be important later. I'm going to need to distinguish two cases. Either this vector lies in the cone itself or not, and we call it incoming if it does lie in the cone, and outgoing otherwise. So it always lies in the linear span of the cone, but not necessarily in the cone itself. Okay, and so what's the point of walls? Well, we get an attached associated automorphism of the torus, or formal automorphism of the torus. So given a wall, I'll just pick an element of the dual lattice, primitive, so that our wall is contained in the corresponding hyperplane. And the wall crossing automorphism associated to crossing the wall is given by this formula. So you'll notice that this is rather similar to the formula we saw before. This is a generalization of the cluster mutation. But here, F is now rather more complicated, could be an infinite power series. Okay. So how are we going to get our scattering diagram associated to our cluster variety? Well, the first step is to define some incoming walls associated to each center of our toric model. So recall that each center can be defined in this explicit way. So you have a toric boundary divisor, and then the intersection of that with a hypersurface defined by a character. And so associated with that, we have a vector V in N corresponding to the divisor, and an element of the dual lattice M, which pairs to 0. So the associated wall is then given by the hyperplane, defined by M, and this binomial function, 1 plus t times z to the v, t being a formal parameter. And this is really completely the same as the wall in Aru's example. So this wall corresponds to the holomorphic disks we see in the interior of our cluster variety U, which are contained in the strict transform of this hypersurface. So it's really completely analogous to the Aru example. Okay, and so now we use an extremely important observation of Kontsevich and Soibelman. So first of all, a scattering diagram is just a collection of walls which is finite modulo m to the k, m being the maximal ideal, for each k. So what I mean is, for all but finitely many of the walls, if I reduce modulo m to the k, all of the functions attached to those walls are congruent to 1, except for finitely many walls. So that means that only finitely many of the automorphisms are non-trivial modulo m to the k. So then we say a scattering diagram is consistent if the composition of wall-crossing automorphisms around any loop is equal to the identity. So the statement of the Kontsevich-Soibelman lemma is the following. So given a finite collection of incoming walls, each with support a hyperplane, there is a unique way to add outgoing walls to obtain a consistent scattering diagram. So this was proved in dimension 2 by Kontsevich and Soibelman and generalized to arbitrary dimension by Gross and Sievert. So this is how we're going to get our scattering diagram associated with cluster variety. I already told you the incoming walls, and now there's some rather complicated inductive but algorithmic procedure to produce the full scattering diagram. So here's the simplest example of the Kontsevich-Soibelman lemma. So I've got 2 incoming walls corresponding to the coordinate axes, and there's one outgoing wall, which is this line of slope 1 in the negative quadrant. But I want to warn you, in general, the scattering diagram consists of infinitely many walls and the attached functions of power series. So here's another example. I won't describe it in detail. But again, we have two incoming walls, but I've changed the attached functions. Now there are square terms attached to them. And there's an infinite sequence of walls approaching this line of slope 1 in the negative quadrant. And if you notice as well, a function attached to this line of slope 1 is in fact a power series. It's no longer a polynomial. And in fact, it gets worse than that. In fact, you can have a scattering diagram that has infinitely many, is everywhere dense in the plane. So a good example of that is just to take a cubic surface, smooth cubic surface, the anti-canonical divisor defined by a triangle of lines in the usual embedding, and the U being the complement. So then, in that case, every rational ray in the tropicalization, just a copy of R2, appears in the scattering diagram. Okay, so to get around that last problem, we use a universal construction, rather simple but useful. So if U is a cluster variety, there's a universal deformation of U with base given by an algebraic torus, just obtained by varying the parameters in the blow-up description. So we're just moving the definition, moving the position of these hypertori we blow up in the boundary. And the total space of this deformation is again a log Calabi-Yau variety. On the mirror side, if V is the mirror of our original variety U, the mirror of this deformation is the universal torsor of the variety V. In other words, if I just write L1 up to L rho for a basis of the Picard group, I take the fiber product of the corresponding C star bundles. That's my mirror V tilde. It's a C star to the rho bundle over my original variety V. And so what happens is it's, well, I'll explain in a moment, but the scattering diagram for script U is actually has a part that's discrete, and it's easier to handle for that reason. So what we'll do is prove the conjecture for this pair and deduce it for the original pair using equivariance. So the functions that we construct on V tilde will be equivariant for the group acting on this torsor V tilde, and so we'll get the conjecture for V as a consequence. So we can take the invariant functions, get the conjecture for V. Okay, so this is the cluster complex. So let's now replace our pair by this modified pair, script U and V tilde. Then the scattering diagram has a discrete part. So specifically, for a toric model, it contains a distinguished chamber, script C. And it's better than that. If I change my choice of toric models, remember the scattering diagram was defined using the choice of toric model, then if I look at the tropicalization of the mutation relating to tori in my cluster variety, then the tropicalization of that mutation maps the support of the scattering diagram for one to the support of the scattering diagram for the other. So the functions change in a sort of slightly non-trivial way, but the support is preserved. And so from this observation or calculation, it follows that if you take the chambers for all the different cluster tori, they fit together to give you a fan in our ambient vector space, n tensor R, the ambient space for the scattering diagram, such that two tori corresponding to related by a mutation correspond to adjacent chambers meeting along a codimension 1 face. So this is the so-called cluster complex, and this was a conjecture of Fock and Goncharov that this complex existed. Okay, and so, yeah, just to wrap this up, in the scattering diagram, if I look in this region, given by the support of the cluster complex, the only walls are just the codimension 1 walls of this fan, and the attached functions are binomial functions corresponding to cluster type transformations. Okay, so here's a sort of a schematic picture of a cluster complex. So the black cones in this picture are cones in the cluster complex. They're approaching these red lines. There's infinitely many of them. And inside this red cone, the typical situation we expect is that every rational ray appears. So somehow this is the very complicated part of the scattering diagram inside the red cone, which I haven't drawn. Okay, so now back to the construction of the mirror. So we can now use the scattering diagram to build a mirror family. So I'll call it script V over A to the R. So A to the R is the affine space with coordinates given by my formal parameters. And we just glue copies of the dual torus associated to the maximal cones in our cluster complex delta using the wall-crossing automorphisms. Remember, those are just cluster transformations. There's no power series involved here. And what we find is that actually we recover the construction of the Fock-Goncharov mirror of U in this way. So this is a justification for the recipe proposed by Fock and Goncharov in terms of the SYZ heuristic. Okay, so now I need to try to describe how we construct our theta functions. That's using something called a broken line, which is a tropical analog of the holomorphic disks in the symplectic description. So I'll begin with a non-zero vector in the co-character lattice n and a point in the associated vector space. So we'll consider a broken line for this data, which is defined to be a piecewise linear path in our vector space n tensor R, ending at the point P, and for each segment, linear segment of the path, there's an attached monomial. So with a coefficient in our ambient ring A and an attached exponent in the co-character lattice n, with the following properties. So the initial monomial is given by 1 times z to the v. The line always travels in the direction given by the negative of the exponent. And at a point of nonlinearity, what happens when we necessarily cross a wall, and the attached monomial before the wall and after the wall are related in the following way. We just apply the wall-crossing automorphism and select a monomial term from the resulting power series. So let's call m gamma the final monomial. And if that was a lot of information, let me just show a picture, schematic picture of what's going on here. So here the black lines are the walls of the scattering diagram, and the green line is this broken line. So it starts off with attached function 1 times z to the v, and it traces a path through the scattering diagram, bending at the walls in this way, ending at the point P, and with attached monomial m gamma at the end of it. Okay, so now our theta functions are defined in the following way. So theta 0 is equal to 1, but for v a non-zero vector, well, we just, for a point in the support of the cluster complex, we define it just to be the sum of the monomials attached to broken lines for this data. And what you can show is that this definition gives functions that are compatible with the wall-crossing automorphisms. So these give local expressions for our function on the dual tori, which are from which this family is glued, and the compatibility tells you, in fact, they glue to give a global function. So this is the tropical analog of our discussion earlier, that we're summing over holomorphic disks some local disk expression, and that gives a global function on our mirror variety. Okay, so here's a couple of simple examples. This is the tropical version of a ruse example. So the difference between the holomorphic disks on one side of the wall and the other are related by this transformation, which is the wall-crossing automorphism. And I don't think I really have time to say too much about this, but this is a slightly more complicated example where we use the second scattering diagram pictured earlier. Okay, and so now I can define my canonical basis, at least formally. So just note that this family we've been considering, the mirror family we constructed, so it's defined over this affine space. The fiber over the origin is just the dual torus. That's just because it was glued from a bunch of copies of the dual torus, but all those wall-crossing automorphisms are trivial modulo the maximal ideal. So we just get the dual torus. And for similar reasons, the theta functions restrict to the characters on this dual torus. Because if I look at the broken lines which bend, the attached monomial is trivial modulo the maximal ideal. So these, just by sort of basically Nakayama's lemma, the theta functions will give a topological basis of the mirror family completed at the origin. Of course, that's not what we really want. We want to have some algebraic results, and we have those results in various contexts, but I want to just emphasize one. So if we assume that this cluster complex that we defined is not contained in a half space, then our theta functions are algebraic and give a canonical basis of the mirror cluster variety, which is just the fiber of this family we've been discussing over a general point. And just to say, well, where does this hypothesis come from? It's related to the condition that U is affine, which is conjecturally necessary, but we don't claim that they're actually equivalent. And it is satisfied in the main representation theoretic examples. So I'm out of time. Thank you very much for bearing with me, and here's some references. Thank you very much.
Okay, thank you. Questions? Okay, so I just have a single question about the hypothesis of the theorem. Is it satisfied? I mean, you mentioned that in the examples that you checked, they're satisfied. The hypothesis is satisfied, right?
So the hypothesis was that this cluster complex is not contained in a half space. So obviously there is a wealth of examples of cluster varieties coming from representation theory. So in those examples, this hypothesis is satisfied. I mean, it's not. Well, maybe what I should have said is that as I wrote the original conjecture, we don't expect a canonical basis in the case where the original variety is not affine. So you can certainly write down cluster varieties where that's not true, and so we expect the conjecture not to hold. But in the main examples of interest to representation theorists, this condition holds.
Okay, so there are more questions. Let's thank Paul again.